with some colleges. So for our next session, let me introduce Leonard Xu, staff engineer and at Alibaba Cloud, who will present accelerate data ingestion in real-time Lakehouse via Flink CDC. This topic will explore how Flink CDC enables seamless real-time data ingestion to power Lakehouse architecture. Please join me in welcome Leonard Xu with a warm round of applause.
Thanks, Jing-song. Hello, thank you. Hello, everyone. It's nice to share my talk. My name is Leonard Xu, and I'm the Flink CDC and connector team leader at Alibaba Cloud, and I'm also the Flink PMC member and committer in open source community. In past 6 years, I've been focused on Flink SQL, Flink CDC, and Flink connector components in Flink community. Today, my session talk is about accelerate data ingestion in real-time Lakehouse via Flink CDC. So my session divides into 4 parts. The first three is why real-time Lakehouse need a Flink CDC, and the second part is about what is Flink CDC. Third part, I will have introduce some best practice of Flink CDC to help users how to use Flink CDC. On the final part, I will introduce the Flink CDC community and our roadmap. So let's start our first part, why real-time Lakehouse need a Flink CDC. Maybe you have heard Flink CDC in today's the session talk, like Jing-song and Shui-Qiang's sharing. So before introduce real-time Lakehouse, I want to introduce traditional Lakehouse architecture firstly. This is a typical traditional Lakehouse. The operational data from application logs and database changes will be ingested to the data lake, and then the data will be processed by computing engine like Spark in batch style between the ODS and DWD and DWS data layer. And as the data lake is open for all OLAP engine, so you can use the OLAP engine to query any data in any data layers. But in traditional Lakehouse, there are 2 shortcomings. The first one is there are 2 shortcomings. The first one is the data freshness is not so good because we use the computing engine like Spark in batch style. So the data freshness usually be 1 hour or 3 hours. And another thing is the CDC support is not so good. If you use the lake format like Iceberg, Iceberg is not good at for changelog. That means when you want to update an existing record. And fresh data is better because that's why we want to propose the real-time Lakehouse. Because the real-time business decision needs the real-time data. So once we replace the Spark batch with Flink streaming, and we can make the end-to-end data pipeline become a streaming style instead of a batch style. So the end-to-end data latency, we can improve from 1 hour to minutes. So, and another benefit is that we change the lake format from Iceberg to Pymon. And Pymon is very good at for changelog process. So we can obtain better CDC support. And the next page is real-time Lakehouse is very fantastic. So how we build a real-time Lakehouse. I think the first step to build a real-time Lakehouse is we need a streaming data ingestion tool because we want to end-to-end low latency. So the first type of your data ingestion tool, we need a streaming data ingestion tool. And Flink CDC is a streaming data ingestion tool. We can recap how to build the entire real-time Lakehouse. The first step is the data ingestion part. We how to ingest data from the message queue from your business database. And the second part is the data storage. You need to choose a lake format like a Pymon, which is good at for changelog support. And the third one is you need to choose a computation engine. For example, Flink. Flink is a streaming processing engine, so you can obtain better data freshness. And the last one is you need a OLAP engine like Storx, which is good at for the real-time data analytics. But today I will focus on the first part, the real-time data ingestion, the Flink CDC. So the today's main story, what is Flink CDC? Flink CDC is an end-to-end streaming data ingestion tool that implements unified snapshot rating and incremental reading based on the CDC technology of database logs. The CDC means change data capture. Imagine you have a MySQL table. When you update your MySQL table or job or delete one record in this table, and the insert and update delete log will be recorded in a binary log file. And then for the Flink CDC, we can read the incremental data from the log, from MySQL's binary log. And for the snapshot data, the snapshot data means the history data of a MySQL table. The history data we can select via JDBC query. We can use JDBC query to select all snapshot data of the MySQL table. And then the Flink CDC can automatically read the incremental log from MySQL binary log. And then for downstream systems like Pymon or Iceberg, Flink CDC can provide a real-time and consistent snapshot. So user do not need to care about how the snapshot data is reading, how the changelog is reading. User only need to keep in mind that Flink CDC is a unified CDC framework that support read snapshot and automatically switch to incremental log reading. Before introduce Flink CDC, let me show traditional CDC ingestion pipeline firstly. In traditional CDC ingestion pipeline, usually need two different systems. The first one is snapshot data synchronize. User maybe need the tools like DataX or Scoop. And for the changelog data synchronize, user need to choose tools like dbtherm or Clio. And the scoop will produce the snapshot table. The snapshot table means the history of the upstream MySQL table. And the increment table means the incremental log of your MySQL table. And then the snapshot table and the incremental table will be merged by your scheduler periodically, like 1 hour or 1 day, and then we can get the finally merged table. But in traditional CDC ingestion pipeline, we need to maintain too many data infrastructures. For example, we need to care the scope cluster, the dbtherm cluster, and we have the scheduler and the incremental table we need to store in message queue like Kafka. So there are too many data infrastructures to maintain. And another shortcoming is the data consistency, because when we merge the snapshot table and the incremental table, the log operation is harder to maintain. So the data consistency is harder to offer a exact nuance data consistency. And the data freshness is also bad because the merge process is according to your scheduler's schedule period. Usually 1 hour or 1 day, the data freshness is not so good. And from a user's perspective, you have to learn and understand so many technology. The data stack is too complex. But with Flink CDC, the ingestion pipeline become simple because we only need one Flink job. Flink CDC pipeline have help user to finish the snapshot reading and incremental reading in one Flink job. So for users, you only need to pull up a Flink job without to care about how snapshot is reading, how the incremental log is reading, and how the merge process is happening. And in this way, Flink CDC is a unified synchronized style, and as you know, Flink can offer the exact nuance semantics. That means we can ensure better data consistency. And Flink can offer the sub-second latency once the Flink CDC job start the changelog synchronize. So, and from user's perspective, one Flink job means the maintain and the learn become easier. This is a Flink CDC pipeline example. So we use the YAML as our API. YAML grammar is very easy and popular. For the example, YAML is used in Kubernetes and Docker. So I think it will be very easy to learn and control for both human and machine. For example, in this example, we want to synchronize a MySQL database to downstream data like Iceberg. We only to define a source part and a sync part, and then we can finish the entire database synchronize. And Flink CDC pipeline support schema evolution by default. So once we start the Flink CDC job via one command, we have a bash script we can start the Flink job by call the bash script. And then once we start the Flink CDC job, if you have any data change or schema change in your upstream MySQL table, and the Flink CDC job will automatically synchronize the schema change. For example, add a column, job column, and data change. For example, insert, update, delete record to downstream Iceberg or payment table. This is the most powerful and interesting key feature in Flink CDC, and some users have asked before. So we call the schema evolution. The schema evolution means if you change the table's schema in your upstream database, for example, add a column, job column, rename an existing column, and your downstream lake table will automatically add a column, job column, or rename the column without manual work. So how Flink CDC achieve the schema evolution? In Flink CDC internal, we support 3 kinds of event: schema change event, data change event, and flash event. The schema change event includes add column, create table, job column event, and the data change event includes insert, update, and delete records. The flash event is a singular event. It's a control event. Flash event is used to flash all in-flight data under the pipeline to downstream external system. For example, if you add a column in your MySQL table, at this time, the Flink CDC pipeline will send a flash event to downstream operators and flash all old data with the old table schema. Once all in-flight data have been flashed to downstream payment table, and then the framework will tell the source, now you can apply the new schema, and then the metadata applier will execute the add column in the payment table. Once the add column table event process finished, and then we can continue to process new data with the new schema. That's a simple example of schema evolution. But Flink CDC support various schema evolution event. For example, add a column, job column, and change the default value, change the column, table, comment, and so on. Another feature in Flink CDC is transform. We support transform like projection, filter, and UDF with SQL-like expression. For example, you want to select, you want to project some fields with a white table, and you only need to define the select clause in your Flink YAML file. And you can also call the computed column. For example, you want to compute the age and subtract the 18, and you can define a computed column. And we have offer some built-in function and also support user-defined function. And we also support define the lake tables primary key and bucket key. And we also support embedding. What is embedding? Embedding is that we support a core AI model in transform. AI is so popular and for Flink is a real-time process engine. In Flink CDC, we support a core AI model in transform, and we have been support OpenAI's popular model. And you imagine this use case, you have data, real-time data in your MySQL table and message queue, and you can read the data to from MySQL, Kafka to Flink, and then you can call the AI model in Flink, and then process the enriched data to downstream Starlocks or Elasticsearch. So I just introduced some key features of Flink CDC. In the next part, I will introduce some best practice to help users how to understand Flink CDC and how to use Flink CDC in your business use case. The first one is synchronize entire database to data lake. So imagine this is the most common use case. For example, you have an application database in your MySQL instance, and in this database, you have many tables with different table schema. For example, you have products, shipment, and others table. And we only need one Flink CDC pipeline to finish entire this table to downstream Iceberg or Paimon. And you will find we in the source part we support in the table part we support regular expression. That means we can match all tables under this application table. And the sync we have support Iceberg, Paimon, Doris, Starlocks, and so on. And the route rule is used to decide what's the destination of the source table data flow. So we use a single table. We use a single table ODS DB. The ODS DB is used to rename the downstream database name, because people usually want to, during the synchronization, people want to change the table name, change the origin database name. And in the root part, you can define your new table, new database name. And another use case, common use case is merge sharding table in CDC pipeline. And in this case, it's we only need to care about the root of the root part. You will know in this case, sharding table is very common when your business expand in a huge scale. For example, we have many user tables start with user 01, user 02, user 03, and we want to merge all sharding tables to one table user. In this way, we only need to define a route rule. The route rule will also support regular expression. You will find in the source table part, we use a regular expression that can match all tables start with user prefix. So all table name start with user prefix will be captured and then merged to the single table ODSDB dot users table. And in this way, you can finish merge all sharding table in CDC pipeline. You only need to write a YAML file and execute one bash script to start the Flink CDC job. And another case is transform. For example, project filter in CDC pipeline. For example, if you have a wait table orders, the original orders have multiple columns, but you only want to select ID, price, and amount on the 3 columns, and maybe you want to filter some records according your customer expression. For this use case, you only need to define your transformer rule. Flink CDC supports the transformer in SQL-like expression. For example, the projection part is used to select the specific fields, and the filter is very like the SQL clause followed by the where part. For example, you can define the filter expression. The price is higher than 100, or the amount is higher than 5. And in this way, the table will be projected, and the table schema will be projected, and the data will be filtered out. Another use case is you can call AI model in Flink CDC pipeline. For example, you can define the AI model. I give an example that I define AI model get embedding is OpenAI's model. Once you define a model in your pipeline part, and then you can call the model in your transform. So in this use case, for example, you have a table named articles. The article consists of ID, title, and content. If you want to generate the embedding vector according the article content, and then you can, in the projection part, you can generate the embedding vector by call the get embedding model. And in this way, in your downstream Elasticsearch table, you'll find embedding vector will be generated and write to downstream Elasticsearch. Once you have the embedding vector, if you want to search some similar article in Elasticsearch, and then you can use the embedding vector. Yeah, and the next part is about our community and future plan. Flink CDC is an open source project from day one, and so I want to introduce our community and future plan. Flink CDC was kicked off at Eureka in 2020, and in 2021, Flink CDC implemented its incremental snapshot framework. This framework is used to unified sync for both snapshot data and incremental data. And in 2023, we introduced the YAML API, and YAML API is an end-to-end streaming data integration tool. And our example in my today's sharing, we use YAML API. And in 2024, we donated the Flink CDC project to Apache Software Foundation. And for this year, we have released 2 versions. The 3.3, which supports AI model in transform, and 3.4, which supports Iceberg connector and introduces the batch mode. Flink CDC community is growing healthy. We have 167 contributors, and over 1,300 commits. And we also reached out 6,000 GitHub stars. For this year, we have released 2 versions, and which involve more than 80 contributors and closed more than 100 issues. And about Flink CDC project's management, as the most active sub-project of Apache Flink, Flink CDC shares same contribution steps as Apache Flink, but we have independent document website. So we offer many user documentations in this website. Welcome to join the Flink CDC community, and you can discuss in Flink mailing list and create issue on Apache Jira under the Apache Flink project. And you can also submit peers on GitHub. The first part is about our future plan. The first one is we want to expand our ecosystem. For example, we want to support Postgres pipeline source and Flux pipeline sync. And in other hand, we want to improve our stability in production. For example, we want to support the configurable exception handle and be compatible with more Flink version. Yeah, that's all about my sharing. Thank you.
Thank you, Leonard, for such a practical, insightful presentation on Flink CDC.